Hello everybody and welcome to today's Interacoustics Academy webinar, which is all about otoacoustic emissions. And today's webinar format takes a slightly different format to our usual style. We are hosting a bit of a Q&A session with Dr. Pete Bray, who joins me today. I will tell you a little bit more about him in a moment. To start with, we've just got a little bit of housekeeping. So as always, everybody's been muted in the room. This is just to make sure that we get a really nice sound quality for everybody. If you are having any problems with your audio experience, please do try looking at the speaker icon at the top of the screen. You should see a drop down arrow next to that speaker icon, and that will allow you to select your headset or speaker option. Sometimes it defaults to the wrong one, so I would suggest that you just investigate that to see that you've got everything set up the way you want. We do recommend that you use the desktop application of Adobe Connect, the platform that we're using. You can come in via a web browser, but the desktop application gives the best experience. And we do suggest that you use a PC or laptop rather than a phone or an iPad if possible, because again, that will just give you a slightly more stable experience. If you have any questions throughout today's session, please do enter them into the Q&A box at the bottom of the screen. And our tech support team are there gathering up your questions, whether they are for our expert today or whether they are of a technical nature, any problems that you're having in here, and they'll do their best to help you out. We are recording today's session, and everybody will receive that recording via email later on today after the session. So if you do miss anything, or you want to catch up or review anything, that is going to be made available to you. We are supplying certificates of attendance for everybody who attends this course, whether that is live today or whether you watch the recording afterwards. You will just need to complete an evaluation form, which we will give you the details on at the end of the session. And then the certificates will be emailed around in about a week to 10 days time. So you've got about a week to complete that form to get your name on the list for the certificates. So my name is Amanda Goodhue. I am an audiologist and one of the international clinical trainers with the Interacoustics Academy. I am delighted to be joined by Dr. Pete Bray with me today, who is the star of the show. He is an absolute specialist when it comes to the world of otoacoustic emissions. He has a medical physics degree and then spent 5 years working as a researcher in David Kemp's team at the University of College London, so getting a lot of very relevant experience. And this led on to doing a PhD in biophysics, and then he's spent the time since really working in research and development in the world of TE-OAE and DP-OAE instrumentation. And we are very fortunate to have Pete working for us at Interacoustics as an OAE specialist and data scientist. So we are delighted to have him with us today. The learning objectives today are really to help everybody to understand the difference between the different types of otoacoustic emissions and to really explore the technical insights into how OAEs are generated and recorded and analyzed. This is really where Pete's area of specialism lies. If there are some more clinical questions, we're delighted in taking those, and I will help out if there's anything that I can add to the story there as well. And we really also want to explore some of the differences and similarities between screening and diagnostic OAEs as well. So hopefully there's a little something for everybody there, depending on what type of role you have, what type of OAEs you use or are interested in using. But for now, let us move on with the show. And we're going to go to our first question. So I should say in advance that we've been taking questions ahead of today's session, and Pete's been working really, really hard behind the scenes to gather these together into sort of themes and collections of questions to then prepare some information in advance. So if we've got questions coming through live today, we're also interested in having those. But for now, we're going to start with some of the pre-prepared questions that we've had come through. The first one, Pete, is all about how the equipment ensures that the same stimulus level is presented in different size ear
Okay, so
canals.
thank
So
you for the
what
kind
can you tell us
introduction.
about this?
During the fitting of the probe in the ear canal, you're presented, or the subject is presented with typically an impulsive click broadband stimulus, and that is useful in determining whether the probe is fitted well in the ear canal. So you'll get feedback during the fitting process of whether the probe is sealed in the ear canal. At the end of that procedure, that same signal is used to adjust the stimulus level. So we call it automatic gain control, AGC. And if I can just show a typical waveform that would be present in the ear canal. So in the top left panel there, we have the click stimulus, a short duration signal. And below that panel is the spectrum of that. And so we can determine whether it's a nice even spectral response. And so instruments do this different ways. Some of them will look at the peak-to-peak height of the stimulus, and after the probe is fitted, they'll just provide a gain adjustment to get the two peaks to be the same height as normal. Other instruments will look at the frequency spectrum in the measurement frequency range of interest, so 500 hertz to 4 kilohertz, and then equalize that sound intensity, based upon the measurement that is seen in that ear canal. And DPs do the same thing. DP measurements do the same thing, but then they have one extra stage after that, which is when the DP measurement starts, it presents a pure tone at different frequencies. And obviously the spectrum that's visible on that panel provides much of the information that's needed. But during the test, we can get slightly more precision by automatic gain controlling each of the stimuli during the measurement. And that enables us, as the measurement progresses, to see whether the probe has moved, actually. So you can get a little bit of a warning that looks like the probe has shifted a little bit. So it's that automatic gain control process that is present in all of our instruments. Yeah.
The next question that we had come through was, what age do you expect to get inconsistent measurements at or near resonant frequencies when we're talking about DP OAEs?
Yeah, and so this problem is specific to DPs because we're using those pure tones. And so what happens is the sound is delivered by the probe. We're trying to achieve a certain stimulus level at the tympanic membrane, but we're measuring that stimulus level at the probe, and some of the sound gets reflected back from the membrane and cancels out at certain frequencies. So we've prepared a little video segment there, if you're ready to roll that, which just demonstrates that in more detail.
So this application has been written just to demonstrate the effect of resonance and how that impacts upon DP measurements, depending upon the ear canal volume. And so we're going to just briefly introduce part of it. And at the top left-hand side, where the mouse pointer is now, you can see the probe fitted in an ear canal, and the ear canal length is represented up there, shown as 0.38 of a centimeter. And I can change the size of that ear canal using the slider just below that. And then in the bottom right hand side, we've got a spectrum, a frequency spectrum, which is derived from the stimulus in the ear canal, and the red dotted line is the energy that's delivered to the tympanic membrane. So that's the spectrum, the frequency spectrum at the tympanic membrane, and the blue line is the spectrum at the probe. And when the ear canal is very small, those two lines are very, very similar. Now, as I increase the size or the length of the ear canal, the blue line starts to separate from the red line, and that's actually indicating that the sound pressure at the eardrum is now no longer exactly the same as it is at the microphone. And that's because some of the energy is reflected back from the tympanic membrane, and it cancels out the incoming sound at the probe microphone. So what we measure at the probe microphone is different now to what's appearing at the tympanic membrane. And that effect varies in frequency depending on the length of the ear canal, because of the wavelength of the sound. And for infants, for neonates, when the ear canal is short, at all the frequencies we're interested in making distortion product measurements, up to 6 kilohertz, there's absolutely minimal difference between the sound level at the two locations. But as the ear canal grows and the child gets older, the effect starts to come in, and you'll see that I've got a little blue line down the bottom there indicating just over 4 kilohertz, and you can see that as the ear canal grows and it becomes an adult ear canal, the sound level, there we go, I've stopped at the kind of 4 kilohertz region. The sound level is now 15 decibels less at the probe microphone than it is at the tympanic membrane. And the reason that's a problem is because it's now impossible for us to know exactly what the sound level is that we're delivering to the cochlea via the tympanic membrane. So we have to estimate that, and different manufacturers do that in different ways. They all try to do this very difficult job actually of knowing what sound level to deliver at that frequency in that length of ear canal. And we do it by trying to identify that looks rather like a resonance notch, and therefore kind of drawing a straight line over it so that we deliver what we believe is an accurate sound level at the ear canal. But that begins to get problematic at certain frequencies once the ear canal gets to a certain length, and there's no defined age when it becomes problematic, because it depends upon how far the probe is inserted into the ear canal and how long the ear canal is, and obviously that varies from person to person. But you just need to be mindful that there will be situations with a large adult ear where the sound level, the target stimulus level, maybe isn't exactly achieved, and to be honest, the consequences of that are not too serious. But if you're doing a longitudinal study where you're wanting to measure how the DP changes over time, it's important that the probe fit is as similar each time as possible, because obviously you don't want to move that resonant frequency around too much between those measurements.
Of how it changes. So thank you for putting that together for us. I think our next question is, how do I identify when there is stimulus ringing taking place? Yes, you are correct.
Yep, and I think, is there a second question? I think we had two that were very similar to this, I think. So the ringing effect in the stimulus is, sorry, can you hear okay? Yeah.
Talking over each other. There were two questions. You're quite right. Yeah. How do I identify when there is stimulus ringing, and how can the ringing of stimulus affect the measurement? A very similar question. So I will hand it over to you.
Okay, so the panel on the top left shows that impulsive response in an ear canal where the probe is well fitted, and the intention is always to try and achieve a very short duration stimulus so that the stimulus doesn't impinge upon the OAE response. And the advantage of that short duration stimulus is that it gives us a nice flat energy spectrum in the frequency domain, so that we're delivering a broadband stimulus presenting plenty of energy at each of the frequencies. And what happens if the probe is not correctly fitted is that the small leak actually acts as a Helmholtz resonator, and so you end up with the column of air in the ear canal resonating out through the leak, and that provides a very kind of tonal response. And in this case, the top right-hand graph there shows a kind of 4 kilohertz typical ring caused by a small leak in the ear canal. Now, that has two problems. The first is it's not delivering energy at all frequencies in a nice, smooth way, in a nice, even way. And the second problem is that the stimulus lasts too long. We're trying to measure an OAE response that starts at around 2 milliseconds. And if the stimulus rings for too long, then it's going to potentially contaminate that response. And so it's really important to keep it as short as possible to make the job of the DSP that much easier. Now, in a clinical diagnostic instrument, you'll be presented with these kind of screens so that you can make that decision yourself. As you're fitting the probe, you can see. But in a typical screening instrument, that that information will be hidden away a bit, and the DSP is performing that task for you. And so we look pretty carefully at different methods to ascertain, to determine whether the stimulus is short enough. And one of those methods is to look at the peak of each of those little stimulus clicks and the ringing, and it should decay away in an exponential fashion. And so an exponential decay, when plotted logarithmically, is a straight line. So we can plot that, and this happens inside the DSP. So, and with that, we can predict when the stimulus is at an intensity that is less than we expect the OAE to be. And you can see there that it's going to be at about 4 milliseconds that all of the stimulus has disappeared. Or sufficient of it has disappeared that it's not significant anymore with the OAE. So, and that's all happening behind the scenes, and that'll just give you a green light. Yes, you're good to go. You can start the measurement. Okay, so this is a DP specific question, and let's just have a quick look at a DP result. So there we have a red dot on the graph, and each one of those has a tick next to it, except one on the left-hand side there, and it has a good signal-to-noise ratio, but it hasn't got a tick. And the reason it hasn't got a tick is because we've not said it's a reliable measurement. And DPs, with TEs, we're using a time delay to see whether it's OAE or whether it's a click. With a DP, it's a continuous measurement, and we're trying to detect a frequency, a single frequency, which may be noise or it may be the DP. And so we need to have some statistical certainty around that. And one way is decibels of signal to noise ratio, but we can enhance that with this reliability measure. So we'll just look a little more detail at that. And behind each of those red dots is one of these measurements. So this is a single DP measurement with two stimuli, F1 and F2, and a series of distortion products, of which the one that's clinically interesting is the 2F1 minus F2. And that blue line is well above the red lines, which are the noise. Now, if we just zoom in a little bit more tightly, so now we've got frequency along the bottom there and decibels along the left-hand side, and the blue is the distortion product and the red are the noises. And we can see the blue is above the red, but we need some mathematical indication of that. And so what we do is we look at the individual noise levels around the DP, and we kind of go, well, there's going to be some noise at that DP frequency. What do we think that would be? Well, probably the average of the ones around it. So that gives us some way of measuring the signal to noise, where that's an assessment of the noise. So I've zoomed out a bit more now, so we've got more noises involved, and I've drawn the mean line in. So the blue is now above that mean line, and the distance between the peak of the blue and that mean line is what we refer to as the signal to noise ratio. Now, in this case, the blue is well above any of the reds, and so I'm pretty confident that's a good measure. Besides, it's got a 12 decibel signal to noise ratio. But if we were to reduce the size of that signal a little bit, it's still got a 7 decibel signal to noise ratio. So it's still above the mean by 7 decibels. But I would be less safe, less secure about that as a measurement, because there's still quite a lot of red lines that are almost the same height. And whereas if that was the result, same mean line, but actually the red now are not as high. And so I would feel that was probably a good measurement. So that kind of thing that I'm doing with my eyes to see whether it looks safe or not, we can do statistically. And the way we do that is to look at the height of each of those noise values and look at the statistical distribution of it. And when we do that, we find that actually the noise values are typically distributed in a normal or Gaussian distribution. And that's very lucky for us, because that we can statistically describe the parameters of that distribution, which is well known. And the number of standard deviations away from the mean tells us what percentage chance that the noise was actually there by chance. And the same thing with the DP. So that distribution of the noise and the distance of the dp away from that mean gives us a statistical reliability function. And if we now put that down the other end of the graph, and you can see it plotted against that data, you can see that the further up the blue is, the more statistically certain it is for that particular set of noise. Now, the advantage to doing that as opposed to just having a signal to noise ratio is that if the test wants to be really secure, supposing you need a 9 decibel signal to noise ratio to get that level of reliability, because the noise is very ragged, then the test will proceed until it's got that sense of that degree of reliability. On the other hand, if the noise floor is quite smooth, the test can stop sooner, and because it's clearly identified as a DP. So it's a way of adjusting how long the test spends to get a very secure piece of data. Good. Yes, that's a tricky one, because there's obviously no set recommendation for this. But one of the issues around TEs is that we're basically deciding whether to include the data or not based upon the size of the signal. And there are many situations where the noise is very much at low frequencies, and yet there's still a good response at high frequencies. So in those certain situations, it's actually quite a good idea to be able to apply some extra filtering so that you can still proceed with the test and at least get something at the high frequencies, even if it's not easy at the low frequencies. So I've got a couple of examples here to show you. So this is a measurement. Both of these measurements lasted exactly the same amount of time. So they're 30-second TE recordings. And one of them uses a standard filter setting. And some of the measurements were rejected due to noise. So that there's not as many recordings in that as we would hope for because of the noise contamination. And if we apply the extra level of filtering, what happens is we reduce the OE at low frequencies and we reduce the noise at low frequencies, but it enables us to collect more data. So the second recording uses a higher frequency filter, and you'll see that the signal to noise has now been improved at the high frequencies because we collected more data. It actually improved at low frequencies too, but the total level of signal went down because we didn't collect as much we were filtering away that low frequency signal. So we've reduced the low frequency energy, we've reduced the low frequency noise, but it's enabled us to collect more data. So the high frequency, you get a clearer response at the high frequencies. Now, really what we should do in that situation is move to a quieter environment, settle the patient more. But in those situations when you can't do that, then apply a bit of extra filtering.
Are you still with us, Dr. Bray?
Yeah, sorry, I had an internet issue, I think.
Can you hear me okay? Now? Perfect. No worries at all.
I have, yes. Yeah,
so our next question was about pressurized OAEs. How do they work and when should one use them?
Okay, so there are certain middle ear conditions, obviously, where there's a pressure offset in the middle ear, and what that does is changes the transmission characteristics of the tympanic membrane, obviously. So it's going to affect the transmission into the middle ear and back out when the OAE is being measured. And I have an illustration here of a series of TE responses that were taken across a range of pressures, and you can see the middle graph is when it's at ambient pressure. And if you look at around the 10 millisecond point, roughly in the middle of that, you can see the signal is at its maximum size. in the low frequencies. At the left-hand side, we're at around 5 milliseconds. The signal hasn't changed very much. And that's because high frequencies still transmit through a more tense membrane than the low frequencies can. So it differentially affects the frequency transmission through the membrane. And we can see that clearly on one of these wideband tympanometry plots, which I'll just break that down into what we're looking at there. And if we slice through that in different directions, the slice on the right-hand side shows a standard tympanometry graph with sort of 226 hertz admittance. And on the left-hand side, we're looking at the absorbance through frequency. And that absorbance plot there is taken at the peak tympanomatic pressure. Now, if we do a standard tympanogram on a patient who's got a slight middle ear pressure offset, so in this case, what does it say, 167, minus 167. So they've got a middle ear negative pressure, and that would affect the transmission of sound at the low frequencies. So we did a DP gram and at ambient pressure, and that affects particularly the low frequencies. So that's the grey line on this graph. And the high frequencies are not particularly affected, but the low frequencies are suppressed by about 10 decibels because of that pressure offset. So then what we can do is apply an equalizing negative pressure in the probe so that now the tympanic membrane moves back to its normal place. It isn't under any extra tension because of the pressure differential, and do another DP measurement, and we can see that actually the signal level has been elevated by 10 or even 15 decibels because that transmission works more efficiently. And so when patients present with some degree of middle ear pressure offset, the probe allows them to do a quick tympanogram and then shift the pressure to provide an equalized pressure across the tympanic membrane to obtain a result that would have been attained if that patient had not got a pressure offset. Yep.
Question: some people will use OAE results as sort of a pseudo PTA, pure tone audiogram. How reliable are OAEs for these type of threshold measurements? Can we use them in that way?
It's always a temptation, isn't it? And I think particularly with DPs, when we plot them on what looks incredibly like an audiogram at times. The answer to this is kind of no, but a qualified no. I mean, at a population level, if you do enough tests of OE level, you will see a correlation with the pure tone, with the audiometric threshold. And I have some data that published data on this from various studies. And the left-hand graph there shows that the threshold of the DP, which is an estimate of the amount of DP, plotted against on the left-hand side the audiometric threshold. And you can see there is a correlation. It's not a bad correlation, but for an individual measurement, if you have a patient turns up and you want to measure their DP at 2 kilohertz and you see that you've got a DP threshold at 20, if you look at that graph, you'll see that could account for an audiometric threshold anything between 5 and 40. So at an individual, you cannot predict. But there clearly is some level of relationship, and other people have extrapolated that or attempted to try that in other methods. So the graph on the right is using a stimulus frequency emission in the hope that was more accurate, and it is slightly more accurate, but still not good enough to give an individual prediction. Okay, and just a quick reminder of what that is. So basically, at a single frequency, we change the level of the stimulus and look at what the level of the dP is. And that can be plotted in one of two ways. dBs, which is the left-hand plot, or more commonly these days as a pressure graph, so that we've got effectively a linear axis on the left and a log axis on the bottom. And that enables us, the points line up in a straighter line typically when we do that. So we can extrapolate that down and predict at what level of stimulus no longer would a dP be produced. And the hope was, once again, that that would provide some kind of threshold information audiometrically. And again, various papers exist to kind of try and evidence that. And it is slightly an improvement on other methods, but it still isn't useful at an individual level. So from a point of view of utility in the clinic, I don't know that we've got strongly demonstrated clinical utility. It's a very interesting tool. I'm sure research interests, but I couldn't give you a kind of use it for that kind of message at this stage. So this is a bit historical. So in the early days, before we had powerful computers and DSPs, we used to look at the waveforms for TE responses and kind of eyeball them and just go, well, that looks like one. And one of the analytical methods that helped us was to look at these waveforms and subtract them and look at the means. So I've got a little video segment on that if you don't mind playing that.
So this is a little web application just to illustrate the AB mean and difference. And what I've done is I've drawn the TE waveforms in the top left-hand panel. And when we collect TE data, we alternate the collection into two different bins, the A and the B buffers, so that we present a stimulus, we record the response, put it into the A buffer, then we do the same thing again, put it into the B buffer, then the next stimulus gets added to the A buffer, and then the B buffer, etc. So what we have are two representations of the response that in an ideal situation are identical, because the response should always be the same. But the difference between those two buffers is representative of the noise. And so here in the top panel we have those two A and B waveforms drawn on top of each other, and you can see one is in orange, one is in blue, and they are slightly different. And this is a real recording, but I've actually made the application so that we can manipulate the difference in the noise a little bit. So in the lower panel there, we've got the correlation, which is how similar those two waveforms are. It's a statistical measure. And as I reduce the noise between those two waveforms, you can see that they get very, very similar, and the correlation increases. So now the correlation is 98.6%. Now, moving that back up to 1, and which is the original exact size, and we can draw the average of those two waveforms. So we add A and B together and subtract and divide by 2. So that's the mean of those two responses. And then we can look at the difference between the two responses. So that's the AB difference, and that's shown in red. And the panel on the left-hand side shows the AB mean and the AB difference, and that's simply the sizes, the energy in each of those blue and the red waveforms. And you can see that the correlation is now 84%, because there is a significant quantity of noise in that recording. Now, that is pretty much how TEOEs were assessed many years ago, because we didn't have the computing power to be able to perform frequency analysis in real time, etc. But now what we do is we tend to look in the frequency domain. And so here's the spectrum of the waveforms, and the top panel shows the detailed spectrum, and the lowest panel shows that energy grouped into half-octave bands. And the reason that's more beneficial and more useful is that if I now increase the noise level in the response, up to 1.5 times actually what existed in this particular measurement, we can see that the correlation is down at 68% now. There's a significant quantity of noise, and that would have been enough if we were just looking at waveforms to say, well, I'm not completely convinced that that's a proper OAE or a good OAE. Whereas when we look in the frequency domain, we can see that the noise was predominantly at low frequencies, and actually there's a very reasonable OE response up at the higher frequencies. So if we're looking for a 2-band pass with a 6 decibel signal to noise ratio, this response would still pass at the 2 higher frequencies bands. But if we had been using correlation, reproducibility, or the AB mean and difference signal levels, we quite probably would have said that's not a clear response. So that's the benefit of looking at it in the frequency domain as opposed to just looking at the total waveform energies.
Yeah, so hopefully this will answer that. So when we are collecting data, most of the signal actually is noise. Okay, so it's a lot larger than the OAE. And so each time a response comes in response to a click, in the case of T or the tones related to DPs, we're looking to see what the size of that signal is. And as I say, most of it's noise, and we reject it if it's too loud. And so I'm going to actually cover this topic specifically on T's because it's a little more easy to illustrate it. But if I collected 2 minutes of data from various neonates, and I analysed in each sample how much noise there was, and I plotted that as a distribution. So along the bottom axis there, we've got the level of noise in each response and the number of them on the left-hand side. So it's a distribution chart, and the level of the OAE was actually down there at around 12, 13 decibels. And you can see that most of the data predominantly was at around 32, 33 decibels, but the quietest it ever was 25, and the noisiest was around 50. And typically what we do is we have a noise rejection threshold, and we accept the data that's less than that, and we reject the data that's above that. And that's fine in a case like this. But not all patients are as compliant as that child, and some of them are very noisy. And so the problem we then have is if we accept the data below that threshold and reject the data above, bearing in mind that the signal is down here, once we've rejected all that data, there's just not enough left in the average. So we can collect for a minute, 2 minutes, and we still don't have enough data. And so the tool for overcoming that is called weighted averaging, or Bayesian weighted averaging. And just a quick reminder of how that works. On the left-hand side there, we've got 2 pieces of data. One is noisy and one is quieter. And we look at the signal level, bearing in mind that most of it is noise. And we look at that level and we scale it. So if it's loud, we scale it small. And in the case of the small one, we scale it bigger. And obviously the small one has got a higher percentage of OAE and a smaller percentage of noise. And so the OAE gets scaled up a lot more. Whereas with the large one, it gets scaled down. And we add all those together and rescale it at the end. And the advantage of that is we get to a cleaner result faster. That's the first advantage. The second advantage is that actually when you look at the noise rejection level setting, the faint red line there is that graph shows the level of noise in the final response. And the faint red line shows the level of noise as you change the noise rejection level. And you can see it's very dependent upon the noise rejection level. Whereas with weighted averaging, which is the dark red line, it doesn't really matter too much what level of noise rejection you use, because the largest noises get scaled down so small that they don't significantly impact on the final result. So you have a lot more of a robust method of averaging. You're far less likely to get the settings wrong, and you get your result faster. So that's what happens, and it happens in TEs and DPs in a very, very similar method behind the scenes. Yes, you can. It partly depends on the instrument, but because when we fit the probe, we're looking for a leak and whether the probe is well fitted. Now, you can put the probe in the ear really well, but if they've got a grommet, they've got a leak at the other end of the ear canal. So the probe may well say, or the instrument may well say, well, that's a leaky fit. The ear canal looks too big, doesn't look like a normal ear canal, and it won't allow the test to start. So then you have to force the test to start, and kind of clinical instruments typically allow that, so that you can press the extra button to say, yes, I want to start. I know there's a grommet. Let's just continue anyway. And when you do that, the chances are you'll be able to make an OAE measurement. Not always, because the reason a grommet was fitted in the first place is because there's some kind of middle ear problem. So if there's still fluid and gunge in the middle ear, then the transmission of the OAE is going to be diminished. But on the other hand, it could be at the far end of their treatment with the grommet, and things are beginning to look pretty normal in the middle ear, and that'll work fine. Yeah, exactly. It's very individual. Yeah.
The stimulus and the response.
Yeah, that's only taken about 10 years of my life, I would say. It's been a challenge because actually the stimulus is 1,000 or more times larger than the response. So in order to give a really certain test outcome, we have to be very careful about how we separate them. So what I've done for this is prepared some little graphics. So this is a measurement just in my ear canal, and that is the ear canal response to the stimulus. Okay, so time along the bottom axis, pressure on the left hand side, and what I'm going to do is keep turning the gain up so that we can get that bigger and bigger. Okay, so here we go. So each time I change slides, the stimulus gets bigger, so we're amplifying it up, and by this point, the stimulus is way off the top of the screen. It's enormous. And we're beginning to see some little details in that waveform at 6, 7, 8, 10 milliseconds. And that is the OAE response beginning to show up. And so I'll amplify some more and some more and some more. And now we've got clearly an OAE that's present, up to 10 milliseconds there. Where does it start? We can't tell because, as you can see, we've zoomed in so much on the stimulus that it's actually where does the stimulus end and the response start. And if I draw on there where the actual response is, you can see that from 6 milliseconds onwards, we can be fairly confident that it's OAE. But we really want to see the high frequencies that come out early on, and they start at 2, 3 milliseconds. So in order to see those, we have to separate the stimulus from the response more carefully than that. And so we're going to use a specific property of OAEs, which when they come from the cochlea, the characteristic growth of the OAE versus the stimulus level enables us to separate them out. So I'll just draw a graph here of the stimulus level in decibels versus the response level. And this is a typical way that it goes. So the more we increase the stimulus, the more the response increases, but less and less as we increase the stimulus. So if we look at that up at the top end with a 10 decibel difference in the stimulus level there, we actually only have a 1.5 dB difference in the response level. And that enables us to construct a stimulus paradigm, a sequence of stimuli, to specifically extract just that non-linear saturated response. So we do that by, in this case, a set of 4 stimuli Three of them are one size, and the fourth one is 3 times bigger. And those responses that are shown on the graph there are all the same size. That's not quite reality. As you saw, that it was 1.5 decibels bigger in reality, which is only about 10% more. So that's the real picture. And when we add all of those stimuli groups together, the stimuli subtract away to 0, because 3 plus 1 minus 3 is 0. But the responses, there's something remaining, and that's called the derived nonlinear response. That's the saturated part of the OAE. And that enables us to completely separate the OAE from the stimulus. I say completely, it's a bit more complicated than that, but actually that's the technique we use to get it so we can see a little bit further back into the stimuli. Yeah, I was just a slow worker. Yeah, so I think it's true to say, well, it is true that the DPs use a more frequency-specific method of stimulation. That's for sure. So we're only putting a single tone or 2 tones in to elicit the response, and the response comes back from a very specific place on the basilar membrane. A TE kicks the whole system at once with a broadband stimulus, and the response that comes back contains all the frequencies that were in the response, and we can analyze those out using spectral analysis and see the frequency specific response. So if we look at a chart there, we can see at the top, that's the frequency spectrum of a TE with all of the little individual noise frequencies, and the green being the individual emission frequencies. And we can subdivide that down as frequently specifically as you like. Typically we don't. We measure it in kind of half octave bands because we feel that's audiometrically important. So the DP only tickles one part of the membrane at the same time, the basilar membrane at the same time, and so it is very frequency specific. That has a positive and a negative effect, actually, in that you can end up with being at a little bit of a null and actually thinking you're measuring at 4 kilohertz, whereas 4.2 would have perhaps been a better frequency. You wouldn't have suffered that problem with the TE because you would have grouped all the data together and seen on those graphs that actually there still was quite a good response there. So I'm kind of voting for TEs here in that they get a bit of an unfair criticism, and then they're kind of not frequency specific. But actually, both techniques now enable you to analyze the response in a frequency specific way. Good. So the advantages and disadvantages, I mean, because of the way we're collecting the data. So with TEs, as we showed in those graphs, it's very difficult to measure high frequency TEs because they come out so soon after the stimulus. So the sort of upper frequency limit for TEs is probably around 4 kilohertz. But because we're measuring the response at the frequency of the stimulus, in this case a broadband stimulus, we can measure lower frequencies with a TE. And the problem is that the noise in the test environment is typically low frequencies. And with DPs, we're measuring at the F2 frequency. So if we do a 1 kilohertz measurement with a DP, the DP itself that we're measuring is coming out at 600 hertz. And that half an octave lower in the noise floor in a noisy environment is a bit more difficult. So typically what we say is that TEs are great from kind of like 700 hertz up to 4 kilohertz, and DPs are more towards the upper frequencies. So let's say 1 kilohertz, depends on the noise environment, but for screening we would push it more towards 1.5K up to 6K, for example. So those are the two differences there. That's a frequency difference. The second difference is with TEs, it's an interrupted stimulus. It's a click and then a long pause, then a click. So the amount of energy that we're able to put into the ear without the click being too loud and unpleasant is a bit limited. With the DP, it's a continuous stimulus. And so we can actually deliver more energy to the ear with DPs. And that enables us to see OAEs from people that've got a greater threshold of hearing. So people with more of a loss can have a DP if you use higher stimuli levels. So a 70 decibel stimulus, for example, can get a DP from somebody who's got a 40 decibel loss. But you would never achieve that with a TE because you just cannot get enough energy into the system. So those are the two main differences. And once you're aware of that, it becomes kind of more obvious which one you should use in which clinical situation. Yeah. 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 Yeah, so that's sort of answered in the last question in a way. So now we've kind of covered the frequency differences, the energy differences. You can end up in a situation where somebody has got a higher frequency or a lower frequency loss or more of a loss at certain frequencies. And so those two different techniques can tease out a response from one person with one technique, but perhaps not the other. So that would be
and a very
the brief
popular
answer to that.
question all the time: what's best to use for screening, TE or
Yes.
DP OAEs?
You should never ask people about religion or politics. And I think it's the same with Ts and DPs, to be honest. I mean, they both have just these subtle differences. Now, years ago, when it first started looking at screening, Susan Norton did an enormous trial to see what was the best technique screening for hearing loss in infants at around 30 decibels. And that's the population she wanted to capture. And she was using TEs, DPs with like a 60, 55 stimulus level, and DPs with a 75 dB stimulus level. And it turns out the 75 dB was just too much energy. They were finding babies that had got a hearing loss of 40 decibels. So that wasn't ideal. So they brought the stimulus level down on DPs to match the sensitivity of Ts. So with a stimulus level of 60, 55, that kind of level in DPs, you're finding exactly the same population of hearing loss in neonatal screening. So then the remaining differences are, what frequency are you wanting to find a loss at? And with TEs, it's a little bit easier to find it at lower frequencies than with DPs. But most protocols have got like a 2-band pass. So if we're looking at half octave analysis between 1 and 4K, both Ts and DPs are going to pop up 2 bands at 2 or 3 kilohertz, 4 kilohertz, with a similar degree of frequency. So I'm not going to come off the fence on this. Indeed. Yeah. Yeah, and I think, over the years, we've kind of come to a kind of a fairly standardized, most people talk about 6 dB, and it's kind of, derived empirically over years. And behind that, there's a lot of science, and it's best at the end of the day to leave the protocol to the manufacturer. So what it's delivered with is probably the best thing. And that's because each manufacturer knows their equipment best, the way they process the noise. And I hope they all do kind of the thing that we do, and I'll just briefly go over this, but we do an enormous amount of testing with realistic noise situations and to discover what is the sensitivity of the equipment. And the sensitivity is, if you imagine you had 100 hearing impaired neonates, what are the chances of how many of those would pass the test just because they were unlucky that the noise that they produced looked like an emission? And that's a very real problem. So if you have a signal to noise ratio that's too low, sometimes the noise will look like an emission. And so we do these tests literally tens of thousands of times on our noise recordings. And we look at what the pass rate is with different numbers of bands and different numbers of signal to noise, and we plot that as sensitivity curves. And that's what this graph is. So the blue line is the sensitivity of the equipment with a 1-band pass. And if you look along that blue line at the 4 decibel signal to noise ratio, you'll see that it's around a 90% sensitivity. So for every 10 hearing impaired children, one of them would pass the test, and that's not good enough. So we would need to increase the signal to noise ratio for a 1-band pass. And if you take it up to 8 decibels, then we're 99% sensitive. So it's only going to pass 1 in every 100. Still not good enough. So then you say, well, it takes a long time to get that level of signal to noise ratio. Let's have a look at what happens if we say 2 bands. So if you do 2 bands with 4 decibels, you're now at 99.9. So that's 1 in 1,000 that are mistakenly passing. And so we can keep adjusting these parameters, how much signal to noise, how many bands, and assess, what is the sensitivity that we want. And most people settle for kind of 6 decibels and 2 bands. And once they do that, you end up with a 1 in 10,000 chance with our particular equipment of having a misreported case in a hearing impaired population of 10,000 people. So the chances of that is very, very small, and that's one we can live with uncomfortably, but we can live with. And there's another aspect to that, which is once you've made those decisions about how many decibels, how many bands, we can look to see what the impact that is on test time. And so this graph shows how long the test takes with each of those different protocols. And so we're trying to find that sweet spot of, we don't want the test to last 5 minutes, but we don't want to make mistakes by making the decision too early. And as manufacturers, it's a big responsibility on us to get that right. And that's why when we deliver with a screening protocol, it's one that we're happy with.
And this is our second Trends in Pediatrics course. So we ran the Trends in Pediatrics course for the first time last year, and it was so popular that we've decided to do it again this year. And each day will have a slightly different topic. And certainly the first 2 days, I think, will be super relevant to everybody in the room today. The first day is going to be all about newborn screening, and the second day is going to be all about auditory neuropathy. And I know we have had some questions come through with people asking about how OAEs can be used when investigating auditory neuropathy spectrum disorder. So I would urge you to come along to that, because there's a short answer and a long answer, and I think it's well worth exploring the long answer, which we will dive into on that day there. If you are interested in the world of balance as well, we have a VHIT webinar with Dr. Cameron Boreen towards the end of May, which is going to be quite a sort of hands-on session looking at video recordings of how to do VHIT and some tips and tricks from Dr. Boreen there. So hopefully you will all come and join us. You can sign up to those events at the Interacoustics Academy website link, which is linked below the webcams in here. As always, thank you all for attending, and I will launch the evaluation form now. I'm going to press a button, and you should find that a website appears in your browser. It didn't just work for me. Let me try that one more time. There we go. Now it's worked for me. Hopefully that's all worked for you. If you complete that evaluation form, you will be sent a certificate in, as I say, about 10 days time. You've got a week to complete the form, so we'll get the certificates out to you. I also have a couple of resources that I'd like to guide people towards. Immediately below Dr. Bray's camera, you should see a box that says download me, and in there's a PDF document titled A Guide to OAEs. That's a document that we've put together at Interacoustics. It's a really comprehensive guide to OAEs, as it says, and it does explore some of the themes that we've covered today about things like protocols and criteria for passing and accepting OAE responses, and it dives into some of the science. So it's quite a useful resource to look back at. Certainly covers similar themes to what we've done today and some slightly different ones. So I'd urge you all to download that and make use of it. There is also a web link right down at the bottom of the screen titled OAE Made Clinical, and that will take you to our OAE universe on our website, which has some more resources and more information. So please do go and explore that. We've put a lot together that will hopefully demystify some of the world of OAE even further beyond what we've been able to explore today. So yes, I think given that we have reached the top of the hour, I think we probably ought to draw things to a close. I'm sure everybody's got clinics to get back to. I'm sure Dr. Bray's got some more OAEs to go and record. So thank you so much to Dr. Bray for your hard work in preparing for today's session. And I'm really sorry to everybody whose question we haven't managed to answer today. I think maybe there's scope to do another one of these sessions one day in the future. I will see if I can persuade Dr. Bray to come back and entertain us again another day. But thank you all for attending, and thank you to Dr. Bray. I think we've had a really fantastic, fascinating session, and I hope everybody's learnt a lot today. But I will just pass the microphone back to Dr. Bray to say a final thank you, but thank you from me. Fantastic. Thank you so much, and we will see you all again one day very soon, I'm sure. Take care and goodbye.
Come back another time if you wish.